Okay, I'm trying this again. My original videos I didn't care for very much, so I'm starting again without having gotten too far into it. Originally, these programming training videos were going to be in person, so I could answer questions and help where necessary, and you guys could see things in person. Um, but because of time constraints and because of how things have ended up being, that's not going to happen. So I thought I'd make videos, and what I'll do is with each video that includes code that makes sense to have a demonstration on a robot, I will make a video of my robot demonstrating that code and include it with whatever I end up posting. That being said, this first round is a electrical system overview. I'm going to be using the electrical system overview that I made for the team's website a few years ago, because it is still relevant. There's a little bit of out-of-date stuff, but we won't go over that in this version of the video. I did last time, but this time we will skip it. That being said, if you do have any questions for any of the videos, you can email me, you can messenger me on Facebook. If you have my phone number, you can text me, but there's only going to be a handful of you that have that. But whatever means you need to get a hold of me, I am willing to answer questions if you have them. So that being said, let's get started. I am just going to use this web page for this video. If you've had an electrical system overview with me before, you probably don't have to watch this again. We're going to be going over the same general stuff, just a little bit more briefly this time. That being said, we're going to talk about the brain of the robot. That's the RoboRio. The RoboRio is made by National Instruments, and it's not the most powerful computer in the world, but it has a lot of open I/O, a lot of open input and output connections that you can connect things up to in order to complete different tasks. Now, the RoboRio itself, if you were to compare it to a modern day device, like a modern cell phone sort of thing, it is uncomfortably slow. So normally you hear computer specifications given in gigahertz in terms of processor speed and gigabytes in terms of storage space and memory availability. In terms of the RoboRio, it is much less fantastic, I guess would be the word I'd use. The speed of the processor is measured in megahertz, a dual-core 667 megahertz ARM Cortex-A9 processor, and the RAM and storage space are both measured in megabytes. There's only 256 megabytes of RAM on the RoboRio and 512 megabytes of non-volatile storage, this being the stuff that you store your programs on. The RoboRio makes up for that a little bit, though, with having something called an FPGA. This is a field programmable gate array. Basically what it is it's programmable hardware. It's a chip that you can program circuits into, and those circuits can be used to perform different functions like keeping time, managing turning digital I/O ports on and off. The FPGA is used on the RoboRio to reduce some of the effort that the CPU has to take in order to complete certain tasks that require some heavy timing. So like PWM timing for motor controllers is not kept by the RoboRio CPU, it's kept by the FPGA because the FPGA is a lot better at it than the CPU is. That being said, there's other information here. There's information about the different ports that are available. We'll go over those briefly as we talk about each section down below. But generally speaking, if you're looking for information on this, you can either use NI's website or you can talk to me. I can explain what everything is used for on the RoboRio if you really need to know. Usually what you'll run into is when you need something and you haven't used it before, you walk up and ask, or you Google it, and you'll figure it out fairly quickly. Moving on, if the RoboRio is the brain of your robot, then the PDP, or the power distribution panel, is the heart of your robot. Now, you may hear me say power distribution board and power distribution panel. You may hear me say PDB and PDP. Originally, the power distribution panel was called the power distribution board. When they switched to the new model, that's this black model, the original one being a sort of bluish color. When they switched to the new model, it took me a while to get used to saying the new term, and every once in a while I still slip and say the old one. So just bear with me on that. They mean the same thing effectively, one just being a little bit newer than the other. The PDP is where all the power distribution happens for your robot. The battery comes in, and then there are connectors on the sides that allow you to connect up motors and sensors and all kinds of other stuff. Each connection has a fuse, and some connections can take some sizes of fuses, and some connections can take others. Really, you're only going to see, for the most part, 20, 30, and 40 amp fuses. And these are just there to make sure that too much current, too much energy doesn't get drawn through one channel on the PDP, because it can damage it if you start pulling too much. The fuses that we use are called snap action breakers, snap action fuses. These will automatically pop and then reset themselves once the current draw comes down. That being said, there's not too much else to say about the PDP. This is where all the power has to come from. You can't directly connect a motor to the battery. You can't circumvent the PDP and create your own sort of distribution system. It all has to come through this at some point. That being said, one thing that's nice about the PDP is that connections are nice and solid, and if you wanted to do some basic monitoring, you can hook the RoboRio to the PDP using something called the CAN bus. This is Controller Area Network. CAN is more commonly used to do vehicle diagnostics. Some of you may be familiar with Onboard Diagnostics 2, or OBD2, which is that connector that all modern vehicles have that allows your mechanic to plug a device in and read engine codes from your car to see what's wrong. The CAN used on the PDP and the RoboRio is very, very similar. Obviously, it doesn't use automotive codes in order to send information back and forth, but it is the same specification. It's the same communication profile. The PDP can't do everything by itself. There are some applications that the PDP is not suitable for. Specifically, the PDP would be overkill for powering smaller devices like your robot's radio. That's where the voltage regulator module comes in. The voltage regulator module shares a 20 amp connection, a fuse, this little yellow thing down here where my mouse is. I can click and make circles to show you where my mouse is at. These little connectors on the end here is where the VRM hooks up, along with two other devices, which one of them we've talked about. The RoboRio connects over here on its own 10 amp fuse. The voltage regulator module is there to help you power small devices. It's for sensors, it's for your robot's radio, it's for LEDs. It basically just takes that connection from the PDP and brings the energy down to a reasonable level. You could feasibly plug smaller devices into the connections on the PDP, but like I said, it would be overkill. Nothing bad is going to happen. If you were to, say, plug your robot radio into a 20 amp channel, which is down here on the PDP, because the radio will only pull as much current as it needs to in order to function. But it's kind of a waste of a connection. You only have 16 of the larger connections on your PDP, and you'd be surprised at how easy it is to fill them up. So, generally speaking, if you're plugging in something small, you want a voltage regulator module. There's one other thing that can plug into that same set of connections as the voltage regulator module in the RoboRio, and that is the pneumatic control module, or the PCM. Pneumatics is using air to move pistons and cylinders and that sort of thing. The pneumatics control module is there to help you control the relays that open and close the pneumatic valves to let air go in one side of the piston, in another side of the piston, that sort of thing. The PCM is controlled by CAN, similar to the PDP if you wanted to get PDP sensing information. It takes the 12-volt input from the PDP, as I said. One thing that's very cool about the pneumatic control module is that it has built-in hardware to automatically sense a digital electronic pressure switch to check the pressure in your air system. And if it detects that the air pressure is too low, it also has another connection for a compressor that will automatically turn the compressor on without you having to do too much in the code to make that work. We won't talk too much about the pneumatic control module in these lessons. I don't think I came up with a pneumatics lesson simply because it's very expensive to get started with pneumatics. With the amount of money that I've already put into my robot, it would be a little bit difficult for me to get all the stuff that I would need together in order to do that and to be able to demonstrate it for you. Generally speaking, pneumatics is not very difficult to get into. It's pretty straightforward. And if we had to set up a pneumatic system, it wouldn't take too terribly long. Moving on, we already spoke about this just a little bit. The robot wireless radio is a standard Wi-Fi access point similar to what you'd have in your house. The access points that we use are a little bit weaker. They're not exactly top of the line, top shelf. You're gonna game on this sort of thing, but it works for what we use them for. Currently, FRC uses robot radios from OpenMesh. These radios are kind of mediocre in comparison to the D-Link radios that we were using before. Currently, there's two models of the OpenMesh radio that are available for FRC teams to use, the OM5PAN and the OM5PAC. These radios are being replaced. There was a request for procurement, request for purchase, otherwise known as an RFP, put in by FIRST to all of their vendors, asking them, what do you have for us? What can you give to us that will act as a replacement for the robot radio while it's on the field? It was actually, for me, it was a fairly interesting read as to what they were asking about. But hopefully we will know by the end of the 2019 season what their decision was. And to top it all off, 2020, we should be getting the new radios and have them available for the 2020 season. That being said, a little bit about the OpenMesh radios. They're fairly average in terms of how far they can go, and it's really not any concern to us, seeing as how we only play on a 54 by 27 foot field. It's a little bit more important when you're practicing at home or when you're doing demos, but generally speaking, indoor range 50 to 100 feet when you're going through a couple of walls, outdoor range 400 feet at good conditions. And then of course you have two ways to power. You can either use power over Ethernet, which is a mechanism by which you use the extra wires in an Ethernet cable to provide power to devices, or you can use the barrel jack connector. A A lot of teams have defaulted to using Power over Ethernet because Ethernet is a latched connector. You have to push a button down to take the cable out unless you really, really reef on it. A lot of teams have switched to doing that because the barrel jack connector, is not very secure. It's very easy during a competition for your robot to get snagged on something and that cable get pulled on even just a little bit, and then you're dead in the water. Your radio's down and you're done for. So a lot of teams have taken to using Power over Ethernet to power their radios. On to motor controllers. Motor controllers are the middleman between the power from the PDP and your motors themselves. They give you the ability to control the speed at which your motors rotate. And some motor controllers also provide sensor feedback. Specifically, the one that is better at this is the Talon SRX, which includes an IDC connector on the top that allows you to plug in a cable, and you can plug in an encoder, a couple of limit switches, that sort of thing. Generally speaking, and this is very generally speaking, in terms of motor output capacity, the various motor controllers that you can use, at least the ones that we commonly use, which are Victors and Talons, they don't vary all that much in terms of like response when you wang on the joystick or something. The difference comes in what they have available that you can connect to and the features that they have. So Talon SRXs have built-in speed control capabilities based on sensor feedback. You can connect to them via PWM, CAN, SPI, UART, whereas Victor SPs, which is another common motor controller, can only be connected by PWM, and they don't have the extra sensor connector capability that the Talon SRXs do. But they both look extremely similar. I mean, these are the two pictures that you see on the screen right now are literally, the top left corner is the Victor SP, and the bottom right corner is the Talon SRX. That being said, the one motor controller that we will probably end up using for our demo robot, if we haven't already started building it by the time this video is released, is the Victor SPXs. These are a relatively new motor controller that includes CAN control along with PWM for the Victors. So still no sensor feedback on the motor controller itself, but you do have that ability to connect to a CAN network, which ultimately can make your robot's wiring look a lot cleaner because CAN is a bus, so you can connect just two wires together through all of your motor controllers as opposed to having what is technically 3 wires or 2, depending on the motor controller that you have. 2 sets of wires or 3 sets of wires that all have to individually go back to the RoboRio for each motor controller. That being said, the next thing we'll quickly talk about is sensors. There's a lot of different sensors that teams will use in FRC. They tend to fall in 2 camps: digital I/O, analog I/O. There are some sensors that sort of transcend that sort of one or the other boxing. That being said, some examples of digital sensors are switches, literally on and off switches like limit switches, encoders, generally used to measure speed and distance, such as like on your drivetrain. Ultrasonic sensors, these send out a ping of ultrasonic sound and waits for it to bounce off an object and come back, and then using the amount of time between how long the message was sent and received, you can figure out how far it traveled with relative accuracy. And then, of course, there's photo switches, which use reflected light in order to act as a switch. So if it sees enough reflected light, it turns the switch on. If it doesn't, it turns the switch off. that sort of thing. Analog sensors, potentiometers, these are usually done to measure fixed rotation. So let's say you have an arm that can only move from like 0 degrees to 270 degrees. I can't dislocate my elbow to go all 270. That would be what potentiometers would be used for. Proximity sensors, they're very, very similar to ultrasonic sensors. They effectively do the same thing, depending on who you talk to. Analog pressure switches, if you remember when we were talking about the PCM has a connector for a digital pressure switch, which basically says, yes, there's enough air, or no, there isn't enough air. An analog pressure switch, what it allows you to do is say, okay, this voltage is coming from the switch, that means this amount of pressure. It basically gives you the ability to continuously monitor the total amount of pressure in your air system, in your tanks, and that sort of thing. And then two that sort of go hand in hand, gyroscopes and accelerometers. Gyroscopes are used to measure angular or rotational acceleration, and accelerometers are used to measure linear acceleration. The RoboRio actually has a 3-axis accelerometer built into it that you can use on your robot. One thing that I never understood when the RoboRio came out was why they included an accelerometer and not a gyroscope. Generally speaking, at least when it comes to FRC, gyroscopes are a little bit more useful. There are some math tricks that you can use in order to use an accelerometer to act like a gyroscope and provide readings about your rotation that way. But of course, that costs you some CPU power in order to do those calculations, and generally speaking, it's not something that your average FRC student is going to be able to quickly do during a build season. You would want to sit down and write it outside of the build season and then make use of it just by cutting and pasting when you needed it during build season. Two more things and then we're done. The driver station, most of you should be familiar with this by now. It's basically just a laptop computer running the Windows operating system with some special software on it that allows you to connect to your robot, either directly through the wireless access point on the robot or via the field by connecting up an Ethernet cable from the field that will automatically allow you to connect to your robot through the field hardware, which is normally referred to as the field management software or FMS. A lot of teams for the longest time were using these little to-go PC things because that's what came in the kit, and that's what Andy Mark sold for cheap computers to use as driver stations. They were garbage. They didn't last very long. They broke really easy. I honestly can't say if First is still using these for rookie teams or if they're distributing something else because I haven't worked with a rookie team in a while. But generally speaking, your average 13 or 15-inch laptop with a 4-core CPU and 4 gig of RAM would be plenty to run the driver station and its associated software. You may be scraping it a little bit on programming just because it might be a little slow, but that's not really a big deal. That being said, the next part is bringing it all together. I had originally drawn this diagram just to give a little bit of an idea of how everything would look if you were to connect everything up the way it needed to be connected up in sort of a home use environment. There is code down below this image, but it is out of date. I need to update it just to make sure that everything is correct, but this is okay. This is on par with what you would expect to see to connect up a basic demonstration of how to get two motors to move for a robot. So as I said in the beginning, if you have any questions, please let me know. In the next video, we'll talk about the basic structure of a robot program, how to make a basic drivetrain move, and we'll also talk a little bit about the switch from using Eclipse to Visual Studio Code, which is going to be the new programming environment moving forward for FRC.